We have a midterm morning. Before that, the homework, I think, what is due today? Let's wait for next minute or two maybe. Any comments you have for the exam or anything? How was the homework?
Okay.
Reasonable.
Seems like it kind of relates in with electric field and magnetic field. How light is can be developed or relativity.
Repeat, please. I did not understand. I'm not saying it's wrong.
Yeah, I was kind of how. I guess how I should say kind of like talks about how the magnetic and electric fields are 90 degrees from each other, which kind of shows light is the same way. The fields are 90 degrees apart from each other.
Correct. Except in light, there is this one more condition, at least for monochromatic light, or in general, I think electromagnetic waves, that the magnitude of the electric field has to be exactly the same as the magnitude of the magnetic field. So the energy is equally stored in electric and magnetic field. Has to be equal. So in this problem, we didn't say that, I think.
Yeah.
So I think probably if the drift velocity went at the speed of light, probably that will happen.
Maybe. Okay.
So it's an extreme situation, but yeah, that's a good way to think as to what happens to light in a similar scenario. In general, how electric and magnetic fields look like in a moving frame. Yeah, and we'll talk about that.
Okay.
It will come by. But this was a, what do you say, a trailer of what to expect, like how you're thinking about how electric and magnetic fields change in a moving frame.
Yeah.
Did it help?
Yeah.
Probably was. The question was in the homework, there is electric and magnetic field that is perpendicular. And in an electromagnetic wave, also electric and magnetic field is perpendicular. So is that very simple? And I was pointing out that in an electromagnetic wave, there is an added condition that the energy has to be equal in both electric and magnetic fields. So the electric field magnitude has to be the same as magnetic field. So that's slightly different, but it's a good way to.
Legalizing.
Yeah, that's a reasonable. We'll talk about this too in more detail.
Yeah, that's.
Like we always talk about length contraction, we talk about time dilation, we talk about how velocity transformed under when someone is moving. But now we want to start talking about how electric field transforms, magnetic field transforms, and in general, all the quantities that we are aware of. So mostly we know classical mechanics and electrodynamics, right? That's mostly what we study. And we want to talk about how these things change when someone is moving.
Reference.
Yeah, with respect to a reference point, yeah. Yeah, with that
Yeah.
limited discussion. Yeah. Okay. So in the context of what Ryan pointed out, we started introducing Lorentz transformation. We didn't derive it exactly, but we talked about how light would look like to two different observers. And I think the idea was so is that there's a slight spherical wave, let's say, and that is observed by a coordinate x, y, z, and t, and another coordinates which is moving with velocity v with respect to the other, and this could be x prime, y prime, v prime, and p prime. And idea was this is z, so the velocity is in the z direction. And we said both since speed of light remains the same, it's a constant, it should look exactly the same. So x squared plus y squared plus z squared minus c squared d squared should be 0 in this frame. And we asked what should the transformation be between the two, so that it looks the same here also. Using Galilean relativity, this doesn't happen. So we said what could be the relation? So the prime is equal to a times z plus I think it's a b times, just for dimensional reasons, we put in a c also there, and c times d prime is equal to, I think we put e, I think e times z plus f times e, right? Substitute this in here, and we got, and we also said x prime is equal to x and y prime is equal to y. And we said there is no change in x and y. This leads to the equation x squared plus y squared plus c plus e squared minus of e z plus f c squared is equal to 0, and this was equal to and we were, I think I made a mistake in this while I was doing this last time. Let me try to be more careful. So it was minus of, I think, x squared minus b squared. Is that correct? C squared, b squared. Is that what we had last time? Maybe I wrote it earlier. It's a plus or minus problem. And then I had 2 times V CT.
That's minus 2C.
Isn't
No, it's the last one, minus 2
Minus.
CCT.
Can be plus or minus, right? Oh, minus, no, wait, plus, right? Oh, here you mean? No? What is-
No, the last term, the 2Z PT. That should be negative.
Why should it be negative?
The place where you define C prime here, the first, second line,
Oh, here,
yeah, AC minus BCT.
ah, I see, yeah, this should be minus. I see. That's how we defined it, is that?
yeah,
Yeah,
Okay, and what about this?
that's
that is a word.
Plus,
That's, okay, why did I do that? Whatever. Reason. Okay.
it's
No,
C prime is C minus CT, VT.
Hmm?
The Z prime was Z minus VT.
Oh, yeah, in the Galilean transformation, then if I set A equal to B, then that gives me the Galilean transformation. In at least, it depends on whether you're going to the left or to the right, it doesn't really matter, yeah. So apparently we chose this, is it? Okay. I don't know why, and this was kept positive?
Yes.
Okay, yeah, okay, so then there is a change. So this was minus. And the rest, everything remains the same, okay. So A squared. And B squared, and this still stays plus. And, oh, so this is now minus CT. AB.
Yes.
It doesn't matter, remember, it's just like saying this prime is going to the right or to the left, it should not matter. And, okay. So if these two have to match, comparing these two equations, I have A square minus B square is equal to 1 F square minus B square should be equal to 1. And AB plus EF should be equal to 0. Substitute this in the first equation. I think I was doing E can be replaced with minus 4F squared is equal to 1. And this implies A squared over X squared times X squared minus B squared to be 1. This implies that A squared is equal to F squared. A squared equal to F squared, which also means that I can have plus or minus. We will pick the plus quantity. Quiz, I think. What would happen if A was equal to minus F? Is that a relevant point at all or not? Like, or maybe I'll postpone that quiz for a moment. Remember, there is 2 solutions here, right? A is equal to plus or minus F. So we will pick the positive, and the idea is that is the negative quantity any? Is that a possibility at all? Here again, we do F squared minus B squared this time. So B is minus EF over A. The whole square is equal to 1. So F squared over A squared times C squared minus E squared comes out to be 1, a square minus e squared is equal to 1. This implies that it again x squared is x squared. No, that's not what I want to do. I would like to do e and e, right? Something else. How can I do it? In e squared over x squared. So f squared minus b. B is e f over a plus e squared over x squared. So I do f squared over a squared is. That again gives me a is equal to f. So nothing new. How can I learn b is equal to e? Maybe put a is equal to f in this substitute way. Yeah, so if I put a is equal to so a square e square is equal to e square f square. So a is equal to f, so this also implies b square is equal to e square, which again means b is equal to plus or minus e. So overall, what we have is that a square so a square minus b square is equal to 1. And f is equal to a, and e is equal to b. So that's all we can do. We cannot go further than this because we have only 3 equations. One of the solutions for this is in terms of a new variable, get a 1 parameter problem, and you set a is equal to cosine hyperbolic theta, and b is equal to sine hyperbolic theta, where theta is some arbitrary. Here a and b are complete random functions, right? Here the only thing we say is that a and b should be functions of this velocity. So that's a new quantity theta, and immediately that is satisfied. So cosine hyperbolic theta minus sine hyperbolic theta is equal to 1. So a square minus b square is equal to 1. So that's surely a solution to these equations, and our equations that means is the prime is equal to cosine hyperbolic theta times z minus, right? So minus sine hyperbolic theta times c times t, and c times t prime is equal to these two are related. So it's sine hyperbolic theta times z plus cosine hyperbolic theta times c times t. Okay. So what is cosine hyperbolic theta and sine hyperbolic theta? So we try to relate it with like Galilean relativity should be valid to a certain extent. So if sine hyperbolic theta was v itself, right? So let's think of for small velocities. So that means to say very small angles, like very small, whatever this angle theta is, if we were to compare this with velocity v over c, then maybe we can connect with this quantity. So our idea would be that for some angles that should become velocity, and what we will do is even the maybe physical connection. Right? Until now, it is purely mathematical. So physical connection of this transformation with what Lorentz transformation is God when you say tan hyperbolic theta, not the sine hyperbolic theta, is equal to V over C, which we will often use the notation beta. That's going to be a parameter or dimensionless parameter that we will talk about. So if that's beta, what is A and B? That's our in terms of V over C. So let's start with B maybe. Right now, we start with A, right? So A is cosine hyperbolic theta. And cosine hyperbolic theta is secant hyperbolic theta. Secant hyperbolic theta is related to tangent hyperbolic theta using 1 minus tangent hyperbolic square theta. Right? Think of it as 1 over sine over cosine. Cosine minus sine is 1, so that gives you back theta. And this is the same as we have like A. So A is 1 over 1 minus V square over C square. This we will use the notation gamma. So that would be the Lorentz factor. Beta is if we put the restriction that everything has to go smaller than speed of light, this was always less than or equal to 1. And this is always greater than or equal to 1. So A is gamma. What is B? B is equal to sine hyperbolic theta. That's equal to cosine hyperbolic theta times tangent hyperbolic theta. And that's equal to cosine hyperbolic theta is A. This is beta times gamma. So our Lorentz transformation is from this point on. If you or then we have said it a transformation, right? There exists at least one transformation in terms of this quantity V over C, which leaves is equal to gamma times Z minus beta VT, or beta times VT if you want, and C times T prime. Let me write this as gamma times C minus beta times gamma times CT, and this is beta times gamma times Z and plus gamma times CT. You can, of course, we still have y prime is equal to y and z prime, but x prime is equal to x. This can be written as a matrix transformation. We have z prime, x prime first. We have x prime, y prime, z prime, ct prime. This is equal to 1, 0, 0, 1, 0, 0. That's 0, 0. And that is gamma minus beta gamma 0, beta gamma. Yeah. Times x, y, v. This is when the reference frame is moving in the z direction. So there is an observer moving in the z directions, another observer staying at rest, and how does the coordinates change when they're making any measurements? That's that. X and Y pretty much stay the same, but that is not the case when in general, like it doesn't mean that everything in the X and Y direction will not change. Sometimes it can happen. So for example, it is possible that one velocity is perpendicular to the other, and then we have this rotational quantities coming in. That's something that you will explore in your homework as to one reference frame is going in the X direction, another going in the Y direction, what will happen. So that's there are interesting effects related to that, but we will keep our discussion as far as explicit calculations go for things going in the same direction, but there is a lot of richness which we are missing just because we are doing it, but we'll keep it simple at this point. In those situations, since this is an identity, it is useful to, at least in our initial discussion, talk about only z prime and t prime, and that's equal to gamma minus beta gamma, and gamma. That's your CT. The idea that cosine hyperbolic theta minus sine hyperbolic theta is 1 is equivalent to saying gamma square minus of some mistake here, right? There's a mistake. What's the mistake? Yeah, so the mistake was I was using the scenario where B is equal to E, right? I don't want to choose that. Remember, there was this plus and minus scenario there. I want to choose B is equal to minus E. So I want to remember there is two solutions that I want to do that because Lorentz transformation deals with this being both minus. So what I want to do is this is not plus, this is minus. And nothing changes. So that minus and minus. But it's cosine hyperbolic square minus sine hyperbolic square theta has to be equal to 1, which is a statement that gamma square minus beta square gamma square is how much is that equal to?
One.
That's equal to 1 because I can take gamma common, 1 minus beta square, gamma square is 1 minus 1 over 1 minus beta square, so that's equal to 1, which is equivalent to the cosine hyperbolic square theta. So the determinant of that matrix is equal to 1. If you have, this is your coordinate transformation, what's the inverse transformation? This is your Lorentz transform, what's the inverse transformation? So what's gamma minus beta gamma? So that's a matrix. What's the inverse of this matrix equal to?
The same thing.
If you're, so the inverse will be in physical terms, you're going this way. So this observer will see that, oh, this is going the other way. Right, so it is equivalent to setting V going to minus V. Right, that will be your inverse transformation. So beta will go into minus beta, so this will become gamma. Beta gamma. Beta gamma times. Yeah, if that would be the inverse transform. So overall, idea is that Lorentz transformation that deals with this. This is different from Galilean transformation by the fact that time is no more the same for different observers. Like when you travel, let's say you're traveling on the interstate at 70 miles per hour. Technically speaking, to the sixth significant digit, your time is not the same. Is that important for our real life situations?
Yeah.
Yes.
What was the question?
So you're traveling on an interstate at 70 miles per hour, which is significantly smaller than the speed of light. But the question is that, does it play a significant role in any of the technologies that you deal with?
No,
No?
well,
Would be very small.
Compared to relativity.
Let's say relativistic correction. So I'm saying this implies that the time is not the same, right? So if you're traveling on an interstate, you're traveling at 70 miles per hour, which is about 35 meters per second to 1 or 2 significant digits. And speed of light is 3 into 10 raised to 8 meters per second. So you're 1,000,000 times smaller than speed of light when you're traveling on an interstate. But my question is that important for any of the devices that you use?
Yes.
Right.
GPS.
So GPS apparently makes, so why is that so? Because the GPS requires a correction. By the time in 1 second, you probably move about a meter or two, like probably more than that, right? You move 35 meters per second, right? In 1 second, you move 35 meters. And within that time, you need to send a signal up to the satellite and then come back. And that time has to be within that amount of time, you should know the precision where your car is. And that requires light to go up to the satellite and come back. And that is significant enough. Notice that how far are you? How far is the satellite, by the way? So that's your Earth. Satellite, what's the distance? How far is the International Space Station? Roughly? Approximately?
Can't remember it all.
About 300 kilometers. Everest is 10 kilometers. International Space Station is 300 kilometers. But all the satellites that you need to communicate with, that cannot afford to stay that close because then it will be traveling too fast. It won't be there all the time unless another satellite comes and replaces it. So you have to go much farther. It's typically about 1,000 kilometers farther you have to go to have a geostationary satellite. A geostationary so that you can keep sending. It's always above you instead of International Space Station flies by in a minute. Have you ever seen an International Space Station flying by?
I've seen plenty of satellites moving across the sky.
Satellites.
Yeah,
That's
satellite.
hard to see usually.
I've seen
In
satellite.
the evening time, you kind of see this little
Yeah, if you see a star.
bright moving star.
But that's usually International Space Station.
Yeah.
Like typically the ones that you see are really close by, and that's the International Space Station. And it moves very fast. It's the fastest moving object in the sky, probably. And it moves around the world in 90 minutes. Right, so that's 1.5 hours. So it moves within a minute or two across the sky. It's it's just a dot that is moving. Of course, it's not interesting, but if you imagine it, it is sometimes very interesting, and you can find the times when it will cross Carbondale in an app. Like they provide it in an app, and they will tell you on this day at this time it will cross, and it is very easy to see. It's very easy to spot. It looks like an aeroplane that is going by.
It's
What-
bright, just
Headlights.
It reflects light from the sun. It doesn't have its own light. Even if it has, I don't think it will penetrate the atmosphere
You just see
significantly.
something, just like see the
But
a
it is, yeah, it is
an
like.
airplane movement without flashing red lights.
Yes, yeah. So And remember, 3 people have been living on the International Space Station continuously. So it's a pretty big achievement for mankind in a sense. Like since I think 2000, there are 3 people living and they're keeping on building it. So every time they go, they take some infrastructure with them and they keep building on it. So it's a pretty amazing feat in a sense.
They had one person live up there for like a whole year.
Whole year, I see. Usually it is 6 months, they rotate every 6 months, so 3 people go there, stay there for 6 months, then the next.
Yeah, usually.
shuttle
but
goes,
there's
usually,
this
but maybe-
One astronaut, he stayed up there.
Possible, yeah, good, so. So anyway, so the point was that is 300 kilometers, but a satellite typically we use GPS for is 1,000 kilometers. So we are talking about 1,000 kilometers up and down, so 1,000 kilometers is about 10 raised to 6 meters. Right, we have already reached, we want to travel 1,000,000 meters and then come back in the amount of distance that you don't make an accident if you want to locate your location precisely. That already gives you that you want to, in 1 second, you want to go that much and come back. You got close to speed of light because you're using light to send a signal and come back. So you need that accuracy for GPS to work. And you need to take care of this. If you don't take care of relativity, GPS will not work as precisely as you need it to be working. So relativity is important. And it is taken care of it. And that is how GPS works so accurately. So all this is true experiment. It's not an exotic transformation just for.
Using
Oh. Why are we using? Is that the question?
Yeah, it has plus or minus.
Yes, so here is, so that was my quiz question. We have Galilean relativity and we have Lorentz transformation, correct? Is there any other relativity possible? Right, so if it is, then you should explore it, right? And it turns out that that's only, at least to our knowledge, there is only 2 relativity principle that really obeys some basic transformation properties. And this seems to be an extra solution. Correct? It seems like, especially when you say gamma is minus gamma, that seems to be, but most probably it's a trivial solution. There is nothing outright coming out of it. So the quiz is find out if there is anything non-trivial out of coming out of this plus or minus solution. I don't expect it, but still check it out. Like you want to be keeping it
Like-
open.
Then how do we decide to use the minus part?
Remember, this is Lorentz transformation was not derived this. They realized that this helps,
Oh, okay.
right? So that's where I said somewhere I left mathematics and I connected it with physics. This is what Lorentz transformation is.
Right, so in order to get to the result, they use the minus.
They want to use that, but then the question comes: is there any other relativity other than Galilean and Lorentz transformations? So that's the quiz problem. That's not an easy problem to choose. For example, one can also say, like, all this has to deal with light, right? Light plays a very important role here, and it has to do with electromagnetic waves. Electromagnetic waves obey Maxwell's equation. So it's understandable that, okay, Maxwell's equation keeps C constant, and there is a Lorentz transformation that came by. But is there anything else that moves with speed of light? Can you have light moves with speed of light? Is there anything else that moves with speed of light? Is there anything else that you know?
Oh, that moves the speed of light. Isn't there a type of particle that moves?
There's no string of it's close to light. It's not.
Yeah, it's near the speed line.
So the claim is that anything that has 0 mass will move with speed of light. But neutrino does have a mass as of today.
Gravitons.
Gravitons, right? And so gravitons is gravitational waves.
So
They also move with speed of light, and they are obeying entirely different equations. It has nothing to do with Maxwell equations. It has to do with Einstein's equations. Completely different scenario, completely different equations. Again, there is the limit. And then you can ask the question, two different speeds coming from two different theories, why should they be the same? You could ask, is it possible to have two maximum speeds? No, right? If it's the same speed, that if one is larger than the other, then the second one loses its maximum speed, right? So the idea is that
So there's,
in
two different, there's a speed line and there's maximum speed for the gravity.
or what I'm trying to say is that here, see, the central theme here was that C is a constant. So we said two frames moving, we want to keep the C constant, and we came with a transformation. Is it possible that there are two speeds that are constant? And there are frames or relativity principle that does that. Again, apparently, according to if you read literature on this, they have to be the same, like just by logical consistency, they have to be the same. But you want to think on that and be more critical about that.
So in this both case, like there's only one Z that can keep the speed constant.
There is only gravitational waves also travel with speed of light. But that should raise a curiosity, why? I mean, these are two different theories completely. Why are they the same? That seems to suggest that Lorentz transformation or relativity principle has nothing to do with Maxwell's equation. It is more fundamental. It is more basic in a sense. That's what the suggestion is that. But I cannot say anything more than that because I really don't know anything more than that. But that's a question one can raise and one can start thinking along that. Is that clear? The motivation that I'm trying to give, that
Yeah,
that there are two speeds, but both have the same speed of light. Is that necessary? What does that imply in a sense? So, or what does it imply with the theories or space-time, basic idea of space-time? What does it imply in a sense? But for our purposes, we have one speed, which is the maximum speed. It could be the speed of light or speed of gravitational wave. In general, the understanding is, again, this is not very obvious. It is a deep, one has to go deeper into quantum field theory, and the implication is that anything that has zero mass has to travel with speed of light. I won't be deriving that here. I don't have the necessary background to derive that here. But in quantum field theory, it is possible to do that in an advanced quantum field theory course. That's a possible conclusion that you make. For our purposes, again, we just have we're working in Maxwell's equation, speed of light, and why is the mass equal to zero? That we will come to later, at least. How does the mass behave in all the scenario? That will be something that we will be able to discuss. Is mass equal to zero a possibility at all? What are the implications of that? We'll talk about that later. Let me know.
You mean that has infinite energy? Not infinite sum.
No, I think the implication is what I meant, at least, or a direct implication is, which is Einstein immediately said, is with gravity. If something has zero mass in Newtonian physics, there is no gravitational interaction between them. But the moment you say that it can have energy, zero mass, then yeah, it's not an implication here. You can show that they will interact with another mass, and you have what is called what is it called? Bending of light.
Lens.
Yeah,
Lensing.
gravitational lensing. Is that a familiar idea?
Yep.
Right, so that comes in. Yeah, let me leave that for a
Einstein.
quiz. Tell again?
And we also follow an Einstein. If you-
Einstein ring, yeah, is that what it is called, Einstein ring?
Yeah, you
Okay.
see stars.
Yeah, so look up gravitational lensing, just see what it is. I think all of you guys at least know the basic idea of that, and let's not, let me not Okay, but what are the consequences of Lorentz transformation? Let me talk about that. So now from this point on, we have Lorentz transformation. That is how space-time is, and space and time transform if you want relativistically. That's all it looks like. So what does it mean, right? So, we are saying we'll keep it one dimensional, z prime c e prime. This is equal to gamma. If I'm in the inverse, it is possible to write beta gamma. Sometimes we'll write beta gamma, sometimes we'll just write gamma. Right? Remember, beta can be plus or minus. So that's z times ct. Let's have a very similar situation. So this is Lorentz transformation. It is good to have an analogy, a completely different transformation, and that's the rotation transformation. And I notice here we are talking about z and t, z prime and t prime, and one is moving with velocity v, right? That's the transformation. How does two observers see each other? And in rotation transformation, let's keep it x and y. Doesn't mean that these things are happening simultaneously. This is x prime and y prime. That's equal to x and y. What's the transformation connecting rotations? And what I mean by that is that that is a frame, x and y, and I rotate it. Right. I look at you guys facing you, and then I rotate a little bit, and then I make an observation again. So I could be measuring the length of this table, and first I measure it by standing this way, and then I measure it again to do the same measurement again. And I talk about how does it transform, and this is x prime, y prime, and that's angle theta. Yeah. What is the transformation connecting these two?
Cosine, sine, minus sine,
Good.
cosine.
So this is cosine theta, sine theta. That is a minus sine theta. And cosine theta. Okay. And now I do the following measurement. So I am an observer. So there are two observers. So first I make a measurement, and this is my x-axis, that's my y-axis. And I'm interested in measuring the length of this table. So I measure the x component of this table. Right? That's my x direction, that's my y direction. I measure the x component of this table. Right, so that's, let's say this is about 1.5 meters. So the x component of this table is 1.5 meters. So x is equal, Lx, so let's say, is 1.5 meters. And then I rotate myself. Now I'm rotated, right? So I'm like this. And again, I'm doing the x component. Notice not the length of the table. I'm finding the projection of this table on this hand. So it won't be 1.5 meters. It is a projection of it. It will be smaller, correct? So it is going to be smaller. So let's say that based on the angle, this come out to be 1.1 meter. Do I get surprised? No, not at all, because you see this table. No, it's not the length, it is the projection of this length that has changed, right? You don't worry about it. You don't say that that is a paradox. Do you say that that is a paradox? Is it exotic? Not at all. Right? But when it comes here, we say that, okay, in one frame, I measure time, so let's say t, or length, let's say z. I measure it to be, let's say 1.5 meters. And z prime changes, it contracts 1.1 meter. And then you say that no, this doesn't make sense. Right? But it should be the same, it's the same idea. Like there is a transformation, the components change. Components are expected to change if there is a transformation. There should be no surprise. This should not even be an experiment. Like this is not a good experiment. If let's say Ryan makes a X component of the length of the table, and Aryan makes the X component of the table, you will never match those things, right? That's not a quantity you even try to match. They are not supposed to match, they are supposed to transform. What should match is the magnitude of the Lx square plus Ly square, right? A good experiment would be where you say, I'll go, let Ryan measure Lx square plus Ly square, find this, and let Abdullah measure L prime square plus Ly prime square, right? Will they match? It will always match, right? That's a good experiment. But here we make a big deal. Lorentz transformation or length contracts. Like that's a surprising result. It should not be a surprise. That's a wrong measurement. That should not be what you should be matching. That's a component. It's a time and space are components of something. So the question arises, what should you match? What's the measurement that you should do that will match between, let's say, between any of these?
Time.
Time will also, time is a component, right? Time is a component. It's like saying Ly prime. Time dilates. Length contracts.
Same thing, z squared minus c squared t.
Minus, you said, it's not same thing. Right? That changes everything.
Isn't it meant to be minus beta minus beta?
You can either say minus or plus, let's say minus, if you want. The inverse, right? Any two observers, I flip it and say it doesn't matter.
And how do we exactly say like Lx is 1.5, the projection of Lx prime is 1.1?
I said some angle, pick an angle.
Yeah, okay, but how do we say Lx squared plus Ly squared is equal?
The length of this table, okay, so y, right? But let's say, so why should it be? So let's say L, so let's start with x prime square plus y prime square, right? So let's do this. What should we measure that should be the same under two rotations? Let's measure that. This is cosine theta x plus sine theta y square plus minus sine theta x plus cosine theta y, the whole square, right? This is equal to cosine square theta plus sine square theta x square plus sine square theta plus cosine square theta y square, and there is a cross term that exactly cancels out. Crucial, like very important that that cancels out. And this is 1, so that's equal to x squared plus y squared. So what remains the same under rotational transformation? The physical length. The length of this table, physical length, not the components. Components will change of a vector, but the length of a vector remains the same under rotations. Is there anything else that remains the same under rotations?
Yes.
Mass, isn't it?
What's it called? The dot
That's
product?
advanced.
The dot product. That's like the angle between.
Very good. Yeah, that's an angle. Angle between the two vectors remains the same. Very good. Angles, right? Or it's not just angle. Angle between two vectors remains the same. That plays an important role.
The dot product would also be.
Dot product will remain the same. Very good. So A dotted with B. Very good. A dotted, so two vectors, A dotted with B. So that's an invariant quantity under rotations. So A will change, components change. B changes, but the dot product remains the same. Very good. Okay. Now we want to ask the same thing here. Right? We know that length contracts, we know that time dilates. But what we are interested in, if we want to compare, physics is all about comparing experiments. One lab does an experiment and you communicate to Europe or anywhere else in the world, and you say that, please send me the information. What do you compare? You don't want to compare length because that contracts. That's a component. You don't want to measure time that dilates. That's a component. But there is something that remains the same, and Aryan said it is the minus, right? You add these two quantities. Let's subtract these two quantities. Why subtraction? Because of this property here. This property here. So let's see this. Z prime square minus C P prime square. That's not a length. Here we understand that this is the length of an object, right? That's the distance we measure in a plane. But this is whatever that is. I don't know. Like whatever that is, let's measure this. And this comes out to be gamma C minus beta gamma CT square and plus, no, minus, right? Minus of minus beta gamma C plus gamma CT square. Right. Cross term cancel out because of the minus term. Yep. Again, that minus sign is important this time to cancel. Here the plus was important because there is a relative negative sign inside. Here relatively there is no negative sign inside, so that minus sign was explicitly needed. And now there is gamma square. And there this is minus, right? Minus beta square gamma square and Z square. Right. Remember, this is equal to 1. Right. So that's equal to 1. And minus of again gamma square minus beta square gamma square times C square T square. This is equal to 1. So that's Z square C square T square. Okay. So this becomes very fundamentally in relativity. The main idea is to look for this length. And Math said it very correctly. We derived this for X and Y, but then we made a big leap. We said that any vector, right? Any two vectors, the dot product remains the same. Here we want to look for dot products. That's what is called a Lorentz invariant. We want to look for dot product, but not in the standard dot product, in the Lorentz dot product. Right? This minus sign. Right here, A dotted with B will remain the same. But here the idea is AX, BX plus AY, BY. Here the dot product is going to be having a minus sign. So let's say that is a Lorentz vector, right? So this is whatever that means. Okay, I want to emphasize that this is not a normal vector. This is a space-time vector, right? One component is space, one component is time. It's not a normal vector. This was a vector in space. This is a vector in space and time. One component in space, one component in time. We will call it a 4-vector very soon. But for now, if you allow me to do this, this is a Lorentz vector, right? Temporary notation that will be equal to AZ BZ minus of C square, or let's say A T BT, right? The component, the Z component of the vector, and the time component of the vector. The dot product of that, that's a good measurement you can do. Okay, so that will be a point we are going to make. So the whole of the next couple of weeks is going to be trying to find out what are such quantities. Like Abdullah said, mass is invariant. That will be one of the quantities we will find out, that mass will remain the same. in this way of doing it, but we want to build those things instead of, so only thing as of now we know is that position and time transform this way, but based on that, what else can we conclude? Where what all remains the same, because only those things we can compare. First, we need to know what's the measurement we can match with, only then we can do an experiment, right? That's the main idea. But let me say a few more things before we proceed forward. Notice what remains the same here is, as far as two dimensions goes, x squared plus y squared. Right, so and that remaining a constant means that, let me say that constant is r squared. Right. That's an equation of a curve, which is a circle. Right. So what this means is that if I draw my x and y, have a circle of fixed radius, every point here is a coordinate frame. X squared plus y squared, when I rotate it, I go to x prime square plus y prime square. As I move on the circle, each point on the circle is a reference frame. And all those references measure the same thing. When I'm rotating my coordinate, I'm basically moving my point along this curve. Is that clear what I'm trying to say? That's the active way of transformation. Instead of rotating the axis, I say, how does this coordinate change? Keep my axis fixed and let my particle or the observation point move. That's called active rotation. Usually we rotate the axis and keep the object stay the same. Now you say that I'm going to keep my axis the same and my point moves, right? And how does that point move? That point will move on a circle. Is that clear? Is the statement clear? If that is the case, there must be a similar curve here in the Lorentz transformation, where if I move my axis, that point moves. And what will that be? Here it is z squared minus c squared t squared, let's say some parameter square, is equal to a constant, right? Is equal to a constant. What's that curve represent? The cone. Cone. I think what you mean is if this was 0, it's a cone. But you said it correctly. It's a hyperbola. This is an equation of a hyperbola. So if you have a CT here, it's usually convention that you do take the time on the y-axis and z on the x-axis. And if this constant was 0, then it is a cone, as Ryan or Irene pointed out. And otherwise, this represents a hyperbola. So as this object goes faster and faster, or for the same, not faster and faster, as you pick your various velocities, you're actually moving your object from here to here to here, and so on. So that's your different V's. As you increase your velocity, it is clear that you approach speed of light, that becomes asymptotic to that, right? So every point on this curve is a signature of this invariance. Here it is very obvious that x squared plus y squared is a constant. You can measure this quantity, right? Here also, it is not very hard to realize what remains the same. This length, that length. Time increases, but z also increases, but the difference is always the same. So it happens in such a way that length remains exactly the same. This is called the geometry of a circle, right? So geometry of a circle. This is geometry on a hyperbola. So this is the geometry. So this is called hyperbolic geometry. Whenever one of the distance is flipped sign, it's called hyperbolic geometry. So in geometry, that is a very interesting idea, which is called the Platonic solids. What are Platonic solids? What are Platonic solids? Have you heard of it?
Tectonic plates.
Yeah, they're also good. Very cool. Very recent discovery. Last 50 years of discovery. Platonic solids are that's a Platonic solid. That's a tetrahedron, right? So you're talking, you want to ask there are how many geometrical objects you can build which has the same edge. So it is the same length, right? Every length here is the same. It's equilateral triangles. But you want to make a closed surface out of it. Okay. So there are 5 Platonic solids, only 5 in 3 dimensions. But let's work in 2 dimensions. So let's make it simple. So we say that we have a length L, and we want to make closed objects out of this length L. Using 2 lengths, it's not obvious, it is a straight line. But if you have 3, a triangle is a possibility. Okay. So if you have 4, then a square is there. If you have 5, pentagon. That's not a good pentagon. Bad pentagon. So 72, right? So right, and hexagon and so on. So there are how many Platonic solids you can build in 2 dimensions? The infinite of them. Okay. Now that's standard geometry. Right? It's basically all possible polygons, but regular polygons. Regular polygons means the same length. Polygon is any length. Now you ask the same thing in hyperbolic geometry, that there are how many geometries that you can build such that they are equidistant. So remember, this is hyperbolic, so your intuition doesn't work, right? It's not like the length. So you have to build, you pick 2 points here. So notice how you draw these things. You have a circle, right? Have 3 points equidistant on the circle, connect them, you get a Platonic solid. 5 points, pentagon, 6 points, hexagon. The point is, do the same thing on this. Okay, and that's your quiz problem. Right? This was suggested by Urek in the math department. And the question is, what are the Platonic solids in hyperbolic geometry? Is the question clear? That's a quiz problem. You don't really have to spend 10 minutes on that.
Could you repeat that again?
Okay. So take a circle, right? That's the x squared plus y squared equals constant. Pick 3 points, equidistant. Equidistant has a meaning in here that a dotted. This is 0. This is the same, right? Make it equidistant, and that's the way of constructing your Platonic solids in 2-dimensional circle. Here, do the same thing. Pick points on this which are equidistant. That's the tricky part, because equidistant means this has to remain the same. So it is slightly non-trivial, but with a little bit of experience, you learn to draw those. Once you have them, then connect those lines. Like you have this, and that's your solid. And the question is, how many are there? How many? Right?
2-dimensional geometry?
In 2 dimensions. Let's keep it to 2 dimensions. You can make it 3-dimensional. you can have Lorentz transformation, hyperbolic geometry in 3+1 space-time dimensions, but you can have it 3+4, 3+5, so anything, you can have as many, this is all theoretical we're talking about. And that's a mathematical problem one can ask and find out and check it out.
Did you solve this problem?
I don't think this is solved. I think that I'll leave it to you guys. I want you guys to think, right?
I will ask him today.
Yeah, ask him today. Yeah, ask Urek. Don't ask me. This was suggested by Urek. I was taking his class on, I think he teaches topology. I think I was sitting in his class a few years back, and in those discussions, this came up. And yeah, I found it interesting. So I'm telling you guys.
And those should be also closed.
Ah, good point. That's probably the key. Should it be closed or not? If this is important, yeah. So the point is Platonic solids, does it have to be closed? Right? Good point. I think that's what it is. I don't think we, yeah, ask Urek. Yeah, ask Urek. And I'll stop here.
How do you,
Yeah.
how do you spell Platonic?
Oh, yeah, Platonic. Plato? Plato?
PLATONIC.
Platonic solids, yeah. It's a quiz, so you can spend 5 minutes to infinite minutes. But minimum 1 minute, or is 0 minutes actually.
How much would you say it's too long? On quiz question.
For assessment, for the points, I think more than 3 minutes is too long. For getting the points. Right?
Because
Don't spend more than 3 minutes if you're trying to earn points. If you're curious, then doesn't matter.
I think I've spent like an hour before or two.
Don't do
just like on the whole-
don't do it because it's due. Do it just for fun. Does that make sense?
Well, yeah.
Sorry if I did not convey that
I know.
properly.
You have
But
too
it will
much free
be-
time.
But it will be useful somewhere. I promise. I think
If I
that's
retain the not the information.
okay. Let's stop. But it is more than 4 weeks now, right?